Okay, this is a recap of today's lesson, March 2nd, and we are doing an application problem for biology where we are investigating the growth of bacteria. So bacteria is grown in a culture and it contains 150 bacteria to start with, and it doubles every hour. Part A says write a function representing the bacteria population for every hour that passes. So we have y is equal to 150, and then our base will be 2 for the doubling, and x is our exponent. And the base of 2 comes from the fact that we have 1 plus our rate, which is 1 plus 100%, which will be 1 in decimal form. So there's our base of 2. So graphing the function, I'm going to start by just doing a quick sketch of the function, and then I'll graph it on my calculator in just a minute. So if I'm trying to find the y-intercept, I would substitute in an x of 0, and that would be 2 to the 0, which is 1. So it'd be 150 times 1, so the y-intercept is 150. If I were to substitute in an x of negative 1/2, then 2 to negative 1/2 would be 1/2 times 150 would be 75. So I'm starting to see the general shape here. So this is going to be 75 for the y there. And if I plug in an x of 1, 2 to the first would be 2 times 150, and I would be at 300. So this is the general shape. And I know my asymptote is going to be at y equals 0 because there is no actual k value. So it's just y is equal to 0. So the general shape looks like this, and again, this is just a sketch of the graph. Okay. Part C says write the graph or use a graph to predict the number of bacteria after 12 hours. Well, we know we can always solve this by plugging in an x of 0. So it'd be 150 and 2 to the, that'd be x of 12. But we want to actually look at this graphically, so I'm going to show you the graphing calculator so you can see what that looks like. Okay, ready to get my graphing calculator. So I am going to just graph my function on the calculator. It's causing a little glare there. So I'm going to have y equals, and I am going to put in 150, my base of 2, raised to the x power. Okay, so I know generally what it's going to look like. Let me go ahead and set my window. That's pretty good for now. And then this is what the graph will look like. Okay, so it's hard to see the graphs. Let's change the window a little bit. So let's just say negative 25 to 25 for my x value. So my domain for the graph that's actually displayed is negative 25 to 25. And then my y's will be let's say negative 300 to positive 300 because we had the 300 on our graph earlier. So this is a general shape of it. Okay, and I'm still not loving the x's there. I'm going to do negative 10 to 10 so I can see a little bit more of my graph, and that should help me out a little bit. Okay, so there's our the 150 that we graphed earlier, so that's where that is on the calculator. Now, it asks for the x of 12 and the y associated with that. So I could actually go across and go up and look at the y that goes with that, but that's going to be hard to see on the graphing calculator. So what I'm going to do is go into the table mode, and that's just second graph, and then I'm going to go to where x is 12 and see what the value is. So 614,400 is the value of y when x is 12. So this is going to be 614,400. And that's the same thing we would have gotten if we had plugged in a 12 and just simplified down. So the next question is, about how long will it take for there to be 800,000 bacteria? So what we're really asking here is, the graph's growing like this. So it's basically asking at what y value, what x value will y be 800,000? So I have two choices in my calculator. I can actually graph it like this and then do an intersection with the line at 800,000. So, of course, I'm going to need to change my scale quite a bit for that. So let me change my window to, I'll go ahead and do 1,000,000 for that. And then -1,000,000. And then there we go. So that should give us a pretty good idea. Okay. Oh, that's too big of an X. Sorry, I meant to change my Y's to -1,000,000 and +1,000,000. Graph that. That should help. Okay. So it's just, it looks a little bit different, but it really is the exact same graph. So what I'm really looking for is where this intersects with 800,000. So on my graph, I need to make sure my 800,000 is graphing. And it's actually a line up at the top, so I don't understand why that's not graphing. So I'm going to do it the other way. I'm not sure exactly what's going on with the graphing calculator. It's not graphing the second function. So I'm going to go ahead and set it equal to 800,000 and subtract it over just like we've done several other times. It's the other way to solve, basically, when you have some sort of function and you're trying to find when it equals a certain value. So now I can go back to the original window and just do, let's see, let's just do -300 to +300. That should be good enough. Now the whole graph has shifted down. So what's going on is it's coming up like this. So in fact, it's probably a good idea to show you. It shifted down by 800,000. I'll just do it like this. That should give us something. Okay, so you're going to see the asymptote. Now I need to know where it intersects the x-axis. So it's going to be second, calculate, and it's going to be when I find the 0. And I can see on my graph here it's between 0 and whatever I have my window set here for, which is 25. So that's usually the easiest way to do it. So second, calc 0. My left bound will be this 0 right here, and my right bound will be 25. And it says to guess, and I do want to guess, so press enter, and it is 12.381. So 12.381 is this answer. 12.381, and it's going to be in the units of hours. So it's growing very rapidly. Starting with 150, it grows to 800,000 bacteria after a little more than 12 hours. So that's about how long it takes. So there's a physical point, XY coordinate pair, which would be at 12.381, comma, 800,000 bacteria. So that's what we just located. All right, the point we found for part C would be 12, comma, 614,400. And in part C, we knew the Y value looking for the X. In part D, we knew the X value looking for the Y, or I think I just said that backwards. Part C, excuse me, we knew the Y, we knew the X, we were looking for Y. Part D, we knew the X, but we knew the Y, but we were looking for X. Okay, now we're going to investigate a new type of function. We got a couple new equations to learn today. This is a little activity that we did in class, and you don't really have to do all this, but I just wanted to kind of show you what we did. Basically, if you invested using the compound investment formula, which we've used in the past, if you invest $1, and there's the 1 for the $1, and you know the formula is 1 plus R over N, and here our rate is 100%, so R would be 1. So it's just 1 over an n of 1, because the first time we do it, we're going to compound yearly. So there's just one compound period per year. And then our exponent is going to be number of compounding periods times time. And there's 1 year and there's 1 compounding period, so it's just a 1. And when you simplify down, you get $2. So if you invested $1 at 100% rate of return for 1 full year, and it compounded annually, which means just once a year, then you would get $2. Now, what this activity does is it kind of increases the speed at which it is compounding. So you can see it starts annually, ends up by the quarter second. So it's approaching something called continuous compounding. And we are basically discovering this value here, which is going to be what we use in our formulas. It is E. And basically it's how much money you would have if you invested $1 at 100% rate of return for 1 full year and it compounded continuously. So we're going to use E in the next few equations. So the next thing I want to do is actually graph E for you, just so you kind of get a feel as to how it relates to what we've been doing. So I would like to graph y is equal to 2 to the x, y is equal to 3 to the x, and y is equal to e to the x. And this is just going to be an approximation because e is approximately 2.7183. And on the calculator, you can see where e is. There's a couple ways to get to e. I can do second ln and just do e to the first power here, and it tells us exactly what it is. Now, it's actually not terminating here as it shows. It's just the calculator doesn't have any more space for that. The other way to do it is with the E button, which is part of the division. It's the blue symbol above the division, and then this just gives you E, so you can manipulate E either way. Many, many times you're going to be raising E to a power, so you would use second ln to accomplish that. And then you would use, if you just need E in a operation like multiplication or addition, you could use the other button. So there's 2 ways to get it. All right. So what I want to show you now is that if I graph y is equal to 2 to the x, which we've been doing in class, we kind of know the basics. It's y-intercept is at 0, 1. 2 to the negative 1 would be a half. 2 to the negative 2 would be a fourth. 2 to the first would be 2, 2 to the second would be 4, so you get the general shape of the y equals 2 to the x equation. Now 3 to the x looks very similar, but when I do 3 to the first I get 3, 3 to the second I get 9, so it kind of grows more steeply or more quickly. It looks something like this, so I'd be up here at 9 for this one. This is y is equal to 3 to the x. Okay, and then e is a value between 2 and 3. So the base is going to be a growth, but it's not going to grow quite as fast as the base of 3, but it's going to grow faster than the base of 2. So it's going to be between these two graphs. So it's going to still have the same y-intercept, but it's going to cross somewhere right between here. So e to the first is 2.7183 approximately, and then e to the second would be somewhere between 4 and 9. So it looks just like this. Okay, so you can see the 3 different graphs, and basically you just have a y is equal to 2 to the x, which doesn't grow quite as quickly as e to the x, which doesn't grow quite as quickly as 3 to the x. So don't let this overwhelm you. It is just a number. It's a growth multiplier. It's just a number. So don't let that stress you out. Okay, we're going to go back to taking a few formulas, writing down a few formulas. Okay, so these are the formulas we're going to learn today. The first is called PERT, and PERT is what you use when you are doing something called continuous compounding, which we kind of already referenced. And it's basically going to be y is equal to p times e to the r times t, where p is your initial investment or principal, Y is your amount of money. Usually it's money, doesn't have to be. Amount of money after time t. And then E is just a number. Don't forget, E is just a number. R is going to be your rate of return. And don't forget, you always put that in decimal form. And then T is going to be time, and it is in years for this. So it's a basic little formula where you have your base of E. It's just a number like 2 or 3. But now the exponent is a little bit different. You have your rate of growth in the exponent, and it's just the way that it works for continuous compounding. So that's the first formula I wanted to show you today. The next formula is very similar to this one, and it is, sometimes I call it the NERT formula, but it's basically a decay formula. So I'm going to say decay formula. So N of T is equal to N sub 0 E times to the power of negative K times T. And I'll tell you what everything is. So this is the amount after time T. This is your starting amount, just like before. Your initial investment, your ending amount. This is the same thing, your initial amount of the substance and your ending amount. And so this will be the initial amount. E is just the number E. K is going to be your decay constant. And T is going to be your time. Okay, so that's the second formula. And we're going to do an example of a couple of these. The third one is a temperature formula. So it's the temperature of some sort of substance like coffee or hot cocoa, something like that, after it's cooled off for a while. So T is the temperature, and I'll tell you what every single one of these inputs means. Now, it looks different, but it is the same basic structure with one exception. T sub S, which is your surrounding temperature, is your asymptote. And if I moved it to the back of the equation, it would look very much like your plus or minus K. The reason that is your asymptote is because you think about coffee that you're drinking, if it's hot coffee, and say you go outside to drink it and it's 80 degrees. Well, if the coffee was already hotter than 80 degrees, it would never actually be less than 80 degrees. It would cool down to the surrounding temperature, and that would be it. It wouldn't cool any below that. So that's your asymptote, essentially. T is your temperature of the substance, whatever it is, and we'll just go ahead and write this as a function. Temperature after time T. T sub S is the surrounding temperature. So let me explain that to you. If I'm drinking hot coffee and it's 20 degrees outside, the coffee is going to cool off more quickly than if I am drinking hot coffee and it's 80 degrees. So that has to be taken into account for this equation. Let me just kind of circle this off. Now, T sub 0 is your initial temperature, so it'd be the temperature of your coffee, for example. And then, of course, T sub S, again, is just going to be your surrounding temperature. So this value represents pretty much like your A in your A times B to the X equation. And then, of course, you have your plus K here. So you can relate it back to this. A would be the differential between the temperature of the substance and the surrounding temperature. B here just happens to be a growth of E. And X, your exponent, is a little bit different here for this formula, and then you have your plus K, which would be your surrounding temperature. So it's like your asymptote, this is like your A, or your coefficient of your base, which is E, raised to the exponent. Now K is going to be your cooling rate, and T is going to be time. So those are the three new formulas you need for today. So one, which we call the PERT formula, and then sometimes I call this the NERT formula. It's almost the same exact formula, but this is for growth, this is for decay. And then the third thing, it is a decay type of problem, but it's specifically for cooling. So this is the third type of formula. Now going to the worksheet that we have. I'll just kind of solve it on a separate sheet of paper because I don't think I have an extra worksheet. But basically, I want to do a couple of quick graphs. The first graph is going to be e to the 1 plus x. So I'm going to graph y is equal to e to the 1 plus x. So this looks a little different, but it's really just x plus 1. So I could rewrite it like that. And this is telling me I'm going to have a horizontal translation 1 to the left. So 1 to the left. So my parent function, let's just review what that would look like. So it's going to cross at 0, 1. E to the negative 1 would be 1 over almost 3. So it's going to be roughly a third, because remember e is approximately 2.7813. When I do e to the first, I am going to get a value that's a little bit less than 3. And then when I get a e to the second, it's going to be bigger, of course. It's going to be between 4 and 9, but we're just kind of approximating that right here. So that's the parent function graph. Now, this one is shifted 1 to the left, so this is going to be pretty straightforward. This intercept will just shift 1 to the left. Okay, so it's just going to be a general growth like this. Now, if I do an x of 0, input an x of 0, e to the first is just going to almost be 3. So the y-intercept is going to be actually 0, e. So this is just a general shape of the graph. And that's good enough for these because you're just having to approximate the actual points anyway, because e is irrational and you have to approximate it. Okay, so number 2 is a little bit different. E to the 2 minus x. Y is equal to e to the 2 minus x. Now, this is not commutative. Subtraction is not. I can't just say x minus 2, but I can say y is equal to e to the negative x plus 2. But when I do that, that's legal. I can do that. And basically, I turned it into addition. And then I'm going to have to factor out the negative because it impacts the horizontal translation. So I'm going to say y is equal to e to the negative, and then I have x minus 2. So it's still a negative x, it's still a positive 2, but now I can see that I have a horizontal reflection and a horizontal shift 2 to the right. So horizontal just means that originally if it looks like this, it will now look like this. It will change the direction of the graph. And then it's also going to shift it 2 to the right. So probably what I'll do for this one is just pick a couple of values to plug in. And let's look at the y-intercept. Let's just kind of figure out where that is. So if I plug in a 0, 0 minus 2 is going to be a negative 2. Of course, that will be negated. So it's going to be e squared. So it's going to be roughly 7 point, let's kind of just put it up here on the graph, roughly 7, let's see, e squared is exactly 7.389. So we'll go with almost, well, about 7.389. We'll just show it like that. Now that's the y-intercept. And remember, it would have gone like this, but it now is going to be appear like a decay problem, and it's also going to be shifted 2 to the right. So that changes kind of where the y-intercept would be. Now, what if I put in a 2? I'm going to put in another value that's going to be pretty easy to evaluate. If I do 2 minus 2 here, I get 0. E to the 0 is just going to be 1. So when I go 2 to the right, I just go 1 up. And that is where your y-intercept was, but it's been shifted 2 to the right. Now the asymptote is still at y is equal to 0, so I can just go ahead and do a quick sketch of this. So there's the function that we would graph. And if you're looking at the worksheet, I think this actually goes with number 3, and this actually goes with number 4 that we did in class. Okay, I want to solve 2 other problems. And I'm going to do these pretty quickly. Now, this is the problem here. Use the formula, which is our PERT formula, to compute the total amount for an investment. This is our principal investment. That's our interest rate. It says it's compounded continuously, and that's how we knew or would know to use PERT, and the time is 6 years. So all I'm going to do is say y is equal to 4,500. That's the initial principal. And then I have nope, I don't. I have E, sorry. So I'm just going to have E, and I don't really need to put that in parentheses, but I have E, and then I have RT. So it's going to be 0.05, this has to be in decimal form, times T, which is going to be 6. And I literally just do that in the calculator. So 4,500. And then E, remember it's second ln. And then I'm going to raise that to the 0.05 times 6. And I get roughly 6,074.4. So 6,074.4, and that's dollars. And that's approximate. All right, so that's number 12. Let's look at, number 11. Let's look at number 12. So this is the other formula that we learned today. And this one's kind of interesting because it doesn't give you a lot of information. It just says use this function, and we know that the half-life occurs in 1,000 years. So what I need to know is the decay constant. So I need K. So I'm going to basically have to use some sort of input and output. Like, let's just go with an n sub 0 of 1. Meaning if I start with 1 gram of a substance and I will end up with 1/2 gram. I could use 1,500, I could use 2 here and 1 here, as long as I'm basically taking half of it. And my base will be E, which is just my number, negative K, which I don't know, I'm solving for that, and then I have my time. Time is 1,000. So it takes 1,000 years for your substance to decay by 1/2. So I need to know that rate. Okay, so how am I going to find this? I'm just going to use my graphing calculator like we've been doing. Now I'm going to rewrite this as negative 1,000x because that's what I'm going to put in my calculator. Subtract over the 1/2. Now these are often very, very small decay rates, so I'll kind of show you how to deal with that. So I am going to do E, and I will raise that to the negative 1,000x, and then make sure to go back down on your calculator and then do minus 1/2. And this is going to be something where I need to usually use a pretty small x value, so I'm going to do negative 2 to 2. And my y's, I can also, let's see, I can have those, let's just start with like negative 25, 25, and see if I can see what I need. I really cannot, so I'm going to change my y's again. I'm going to make my y's smaller, let's say negative 5 to 5. I didn't mean to change my x's. Make this negative 5, 5, and graph that. Now, I can't really see exactly where it's crossing. What happens with these very often is it's actually very, very close to the y-axis is what's happening. And I could figure out the x-intercept. The x-intercept would be negative 1/2. Sorry, the y-intercept, sorry, should be negative 1/2. So let me even change this again, negative 1, 1, so I can see this a little bit better. No, it's actually positive 1/2, sorry. So it should be crossing the y-axis right here, but it's just a very, very close to the y-axis there. Now, let me do one thing here. Let's kind of trace along so you can see what's happening. So see, there is my y-intercept that we just talked about. And as I go to the left, it kind of just takes me off the graph, but I am crossing over. So my graph's actually doing something like this, crossing at 1/2 and then going down and coming over. I need this x-intercept. That's really all I need. And I can see it's between 0 and 1 because that is my window here. My window is negative 1 to 1. So I'm going to do second, calculate, and I'm going to do 0, and I'm just going to do 0, 1, because that's the way my window is set, and it's going to tell me it's 0.000693. So K is going to be 0.000693. And very often the K rates are very small like that. All right, and that is the lesson for today. And your homework is posted on the website, so you can just take a look at that and come in the morning if you have any questions.